Welcome to The Explainer. Today, we're diving into an absolutely fascinating intersection of human biology, hardware, and artificial intelligence to explore how we can, quite literally, feel sound. We're looking at a massive paradigm shift in how we interact with the digital world, so let's jump right in.
What if you could physically experience the rhythmic crunch of footsteps on gravel, or the heavy, mechanical drone of an airplane engine right through your fingertips, instead of just hearing it? Now, I know that sounds straight out of science fiction, but this translation of audio into tactile sensation is exactly the puzzle researchers are cracking right now.
Here's our agenda for today. First, the mechanics of touch. 2, the hardware of haptics. 3, the audio-to-touch gap. 4, enter the Sound2Hap AI. And 5, the future of feeling.
Starting off with Section 1, the mechanics of touch, understanding our fingertips. To understand how we feel anything at all, we really have to start with our biological mechanoreceptors, those tiny sensors right beneath our skin, in a field called tribology. Basically, this is the science of interacting surfaces in relative motion. When your finger touches a screen or a haptic device, researchers are actually analyzing how the exact topography of your skin physically interacts with those surfaces to generate the sensations of friction and pressure.
And get a load of this! The microscopic ridges and valleys of your fingerprints aren't just there to help you grip things, they actually change your physical contact area by a massive factor of 3, just depending on how you press down. Our biological sensors are picking up highly complex topographical data every single millisecond, so you can imagine any artificial vibration we create has to be incredibly precise to fool our brains.
Moving on to Section 2, the hardware of haptics, how machines simulate touch.
You've probably heard of some of these. We've got ERMs, or eccentric rotating masses, LRAs, which are linear resonant actuators, and piezo actuators. These are the tiny mechanical workhorses making your phone buzz and your video game controller rumble. They do a great job turning electrical signals into physical movement. But here's the catch. How do we know exactly what electrical signal to send them to perfectly mimic a specific real-world sound?
Which brings us to Section 3, the audio-to-touch gap, the sensory mismatch.
Human hearing is incredibly expansive. We can perceive frequencies from a low, deep rumble of around 20 Hz all the way up to a piercing 20,000 Hz. That is just an enormous spectrum of audio information that our ears and brains are processing instantly.
So here is the fundamental engineering wall. How on earth do you cram the rich 20,000 Hz spectrum of a barking dog or a symphony into a tactile bandwidth that tops out below 1,000 Hz? Our sense of touch literally just cannot process those high frequencies. If you pipe raw audio directly into a vibration motor, it just feels like a numb, buzzing mess. It's a massive sensory mismatch.
Let's look at Section 4. Enter the Sound2Hap AI, a data-driven breakthrough.
Well, before this AI breakthrough, researchers were relying on algorithms that honestly only worked in very strict niches. For example, pitch matching was fantastic for discrete, short events, like a mouse click. Frequency shifting worked pretty well for continuous mechanical noises like a washing machine, and a program called HapticGen excelled at rhythmic soundscapes like ocean waves. But the moment you tried to apply them outside of their specific lanes, they completely fell apart.
And because there was no consistent winner among these traditional methods, researchers really hit a wall. A method that made a digital gunshot feel amazingly realistic might make a digital rainfall feel entirely confusing. They realized they needed a totally new approach, one centered entirely around actual human perception, rather than rigid mathematical rules. So, they executed this brilliant, rapid-fire 4-step process. First, they took 1,000 environmental sound clips and ran them through those older algorithms. Second, they had 34 actual humans hold a vibration actuator and provide 8,000 ratings on which vibrations genuinely felt like the sound they were hearing. Third, they fed this massive dataset of human preference into a deep learning autoencoder. And finally, they used this trained AI to synthesize brand new, highly realistic vibrations from audio it had never even heard before. Now, the researchers actually created 2 distinct variants of this AI. One learned strictly from the absolute gold standard. It tried to replicate only the single highest rated vibration for any given sound. The other variant tried to, please everybody. It took a weighted average of all the different user feedback to try and blend the strengths of multiple algorithms. When they tested these models on completely new sounds with a fresh group of users, the results were totally definitive. Both AI models left the baseline algorithms completely in the dust, but the top pair model actually won out overall. Why?
Well, it turns out that blending vibrations in the preference-weighted model sometimes muddied the waters and smoothed out the sharp, distinctive details of a sound. The top pair model, by learning from just the absolute best single example, was vastly superior at precisely rendering rhythm and intensity.
Finally, Section 5, the future of feeling. Why this breakthrough matters.
The real-world applications here are absolutely huge. Not only does this mean deeply immersive virtual reality and gaming where you literally feel the world around you, but it crucially provides a massive new frontier for accessibility. This tech offers a way for deaf and hard-of-hearing individuals to dynamically feel environmental cues, like approaching footsteps, a honking car, or falling rain, translated perfectly to a haptic vest or wristband. And because the AI generates these textures in under 1 second, sound designers can deploy it rapidly without hours of manual tweaking.
By prioritizing human ratings over strict math, the AI is doing something really profound. It creates textures that we intuitively understand and connect with emotionally. As one user study participant noted, it captured the intensity of a fire crackling in an amazingly realistic way. It goes way beyond a simple buzz. It translates the emotional weight of an environment directly to our skin.
As this incredible AI-driven technology integrates into the devices we hold, wear, and interact with every single day, it leaves us with a really exciting question about how we'll experience the digital world going forward. When the barrier between audio and touch is completely erased, what environmental sound would you most want to feel?